Chapter 8, Section 4, The Determinant and Non-Trivial Solutions. This section focuses on understanding the critical relationship between the determinant of a matrix and the solutions of a system of linear equations. Here's the main question we aim to answer. How does the determinant of a matrix influence whether a system of linear equation has non-trivial solutions? We will explore this question step by step, starting with a brief overview of linear equations and matrices, and then connecting these ideas to the determinant. Let's break our discussion into three parts. Linear equations and matrices, the basic structure of linear equations and their representation in matrix form, the determinant's role, understanding the thematical significance of a determinant. Non-trivial solutions, the conditions under which non-trivial solutions exist. Let's begin by revisiting the basics, the relationship between linear equations and matrices. A linear equation is an equation where each term is either a constant or a product of a constant and a variable. This is a single linear equation containing three variables, x, y, and z. When we have a set of such equations, we call it a system of linear equations. The goal is to find the values of x, y, and z that satisfy all these equations simultaneously. Solving these equations directly can be tedious, especially for large systems. Fortunately, we can represent the entire system in a compact form using matrices. Here, A is the coefficient matrix containing the coefficients of the variables. V is the variable vector containing the unknowns x, y, and z. B is the constant vector containing the constants on the right-hand side of the equations. For our example, using a matrix, we can express a system of linear equations in this way. Sometimes, the system of equations has no constant vector on the right-hand side, like in this case. This is called a homogeneous system. The solutions to this system depend heavily on the properties of A, and this is where the determinant comes into play. Let's recap determinant. The determinant is a scalar value associated with a square matrix. For an n by n matrix A, the determinant is denoted as DETA. It encapsulates important properties of the matrix and has a profound connection to the solution of linear systems. The determinant can be thought of as a measure of how the matrix transforms space geometrically. It also works as a signal of whether the matrix is invertible or not. Let's consider a case where determinant is not zero. If the determinant of matrix A is not zero, the following properties hold. First, the matrix A is invertible. Second, the columns of A are linearly independent. That is, no column can be expressed as a combination of the others. Third, for the homogeneous system, the only solution is the trivial solution. That is, V equals 0. In other words, there are no non-trivial solutions. This is because a non-zero determinant implies that the matrix spans the full n-dimensional space, leaving no room for free variables. Next, let's consider a case where the determinant is 0. If the determinant of matrix A is 0, the situation changes. First, the matrix A is not invertible. Second, the columns of A are linearly dependent. That is, At least one column can be expressed as a combination of the others. Third, for the homogeneous system, there exist infinitely many solutions, including non-trivial ones. This happens because the zero determinant indicates that A does not span the entire n-dimensional space. Instead, the solutions lie on a lower dimensional subspace. In the context of data science, the existence of non-trivial solutions suggests their dependence among variables. Non-trivial solutions indicate that there are dependencies among the variables, as not all columns of A are independent. So, it suggests the usefulness of applying dimensionality reduction to the data. Let's summarize the points of this section. When the determinant of a matrix A is not zero, the transformation represented by matrix A maps all vectors uniquely. So, only the trivial solution satisfies a v equals 0. When the determinant of matrix A is 0, the transformation collapses the space, creating dependencies among rows or columns. In this scenario, there are infinitely many vectors v that are mapped to 0, creating non-trivial solutions. Thank you for watching. Please thumbs up and subscribe to my channel.